My name is Hazim Gaber, and we're going to continue with our structured cabling systems course. And today we're going to talk more about fiber optic cable design. So last course we talked about the choice between single mode, and multi-mode. And we thought about attenuation, i.e. signal loss on the fiber. And we know that it's equal to the cable loss in dB per kilometer plus number of connectors plus number of splices. So when you've designed the system, you know how long is my cable, how long is the cable, and how many connectors do you have, and how many splices do you have. And then based on that, you get a total loss. So once you've figured out what loss you're going to have, then you can decide on how powerful a transmitter. And actually, once you've decided on that, then you also need to think about the bandwidth you require. And then you can select a fiber that can support the bandwidth and select a transmitter and a receiver that can support the loss. So we can rewrite this formula to say that max length equals. So we can rewrite the formula as max length is equal to the maximum tolerable attenuation minus losses from connectors minus losses from splices. Divide all that by the cable attenuation coefficient, which is loss per kilometer. So, in order to measure our system, we want to look at bandwidth and then attenuation. So the bandwidth you already know. So you say you need a gigahertz, for example. You need 10 gigahertz. Or you need 2.5 gigahertz. So these correspond to, say, a gigabit per second, 10 gigabit per second, 2.5 gigabit per second. And then attenuation. So remember, I have a receiver and I have fiber link and I have a transmitter. And this distance could be 1 kilometer or 2 kilometers or 300 meters or whatever. And then our transmitter has a certain power. So let's say it's, plus 7 dBm, or it might be negative 5 dBm, etc. And our receiver has a sensitivity, so maybe it's plus 20 dBm. So first thing we want to do is calculate the gain. So let's say, transmitter plus receiver. So maybe plus 7 dBm plus 20 dBm. So we have 27 dBm gain on our system, which is pretty good. I mean, if you use an LED instead of a laser, you may not have the same gain. You may have 10, you may have 5, whatever. And then you have something called power penalties. So there's like an operating margin, because say our gain was 0, say there's got to be a margin for error, because say this receiver is operating at plus 20 under ideal conditions. If we had no room in the power budget, we wouldn't be able to, and this receiver was not operating at optimal conditions or wore out, or same with the transmitter. What if the transmitter was operating today at plus 6, or a receiver was operating at plus 19? So we have to have an operating budget, which can vary from spec to spec, but assume it's about 3. And then we also have what we call a repair margin. So it's possible for the fiber to get cut later on and needs a splice. In that case, we have future splices, for example. So plus 0.6 dBm, for example. So we have a power penalty of 3.6 dBm. And then we now have what we call a link loss budget, which is the gain minus the power penalty. So we were plus 27 minus 3.6. So we're at 23.4. So that's our budget. So if we're designing a fiber optic system based on these transmitters, we can afford to lose up to 23.4 dBm, and we still have an operating budget of 3.6. You can think of it like a financial budget. You know, you have $1 billion and you have expenses of 900,000, and you can still afford to have a little bit of money in the bank in case of unforeseen expenses. So we know then, number 4, what is the loss per kilometer? So we want to figure out, let's say our fiber is 4 kilometers long and we lose 0.5 dB per kilometer. So we lose 2 dB m. 2 dB. So then we also have connector losses. So let's say we have 2 connectors times 0.75 dB per connector, which is 1.5 dB. Now, if your fiber link goes to a patch panel or a cross connect somewhere, you may have more than 2 connectors. So in my example, I just drew a straight fiber. But you may have fiber, so you have a receiver, and you have a connector, obviously. And then depending on, this was a mechanical connection, you may have a splice. If it was a mechanical connector, you won't have a splice. If it's not, you may have a splice. Depending on how complicated the run is, you may have other splices, or you may have cross connect. You may have another splice, and then connector, and then your transmitter. So splices don't use up much of the budget, but connectors do. So now we lost 3.5 dB, plus we have a splice loss. So I'm going to say 0.3 dB times 2 splices, which is 0.6 dB. And so that gives us 2, 3, 4.1 total. So we're doing pretty well here because we've got 24.3, 23.4, right? 23.4 dB budget. And then 4.1 dB physical loss. Which gives us a margin of 19.3 dB, which is pretty good. So when we test this fiber, we want to make sure we actually get the 19.3. Now, if you design a fiber and it turns out that your loss is much higher than your budget, then you're screwed. So you have to go back to the type, think about the type of transmitter that you're using, and think about the type of receiver that you're using, and buy something more powerful. Because, I mean, these are like typical, like these are pretty powerful, but say even on a decent single mode, you should be able to get a gain of about 15, even with a budget of a loss of 3 or 4. So if your link loss budget is say 15, and you've got a couple of connectors and a couple of splices, you should still be able to get 11 or 12 as your loss, and then as your loss budget, and then 11 or 12, that gives you, what did we say here, loss per kilometer is about 0.5. So still can do about 20 kilometers. So if you're finding that your loss is too high, you probably are using a multi-mode fiber, or there's something wrong with your calculations, especially if the fiber is not that long. So just think about it. So we're saying that this budget, this is the maximum loss that you can have on the end-to-end cabling system. Now, when you go to certify a fiber, you're not going to, it's not going to pass certification with a loss of like 19. The your 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 tester is going to look at the length, and it's going to ask you the number of connectors and the number of splices, and it's going to use basically the TIA standard. So if I install the 4 kilometer long fiber, my tester is not going to accept a loss of 19 dB. It's going to accept a loss of 2 plus the 1.5 plus what we calculated here, 4.1. So if we get a loss on our fiber of more than 4.1, then we're in a lot of trouble because that fiber is not installed correctly, which means we either got some bad splices or we got some bad connectors or the equipment's not clean. I mean, if you think about it, when I do a fusion splice, I get a loss typically of 0.01 dB. So, I mean, that's practically nothing. And if so, typically when I run my fibers, if it's a short distance, we just splice what we call pigtail on the end. So we've got 2 splices and 2 connectors plus loss per kilometer. And so if we lose, 0.75 here, and we lose 0.01 here times 2, and we can tolerate up to 0.3, we've got a huge margin on the actual fibers. And that's important. So I go back to what I said was the power penalty. I'm going to talk a little bit more about the power penalty. And we want to know we can get these from, I just assumed 3 dB, but you get them from the SFP manufacturer. There's a spec. And so use 2 dB for an LED and 3 dB for a laser if there's no spec. And the reason we have a power penalty is because there's always variations in the quality of the transmitter. Transmitters wear out after some time, the receivers wear out after some time. So we also are thinking about whether we cut the cable at some point. We may need to splice it. So, and I said 2 splices. We should assume 2 splices here, but we may get 3 splices or 5 splices. So think about the likelihood of your cable being damaged and how many splices are going to be required. And then the other thing we need to think about is temperature, because temperature affects it by up to 2 dB per kilometer. And then splice losses. I mentioned earlier that the splice loss was 0.3, but that's actually the maximum, which is 0.3 is maximum. But you can have a loss of 0.01 to 0.05, which is average. So if you wanted to, if you had a cable with a really tight margin, you may consider using a lower value. So as I said, if we built a cable and the attenuation is more than the margin, this cable is going to fail. Simply not going to work because there's too much loss on the cable for us to be able to transmit a signal that will be readable on the other end. So think about either using more powerful transmitters and receivers or cutting out, reducing the number of splices, reducing the number of connectors, or maybe you have to add a transmitter receiver amplifier somewhere in the middle. There's also one more thing we have to think about too, because you can have a system with too little loss. So if the receiver has a range, and then if our gain, for example, our range is 20 dBm, and our system law budget is 23, or sorry, our gain is 23, then that means that we've got too much power for our receiver. We'll burn our receiver. So we need to adjust the power on the transmitter. Or use an attenuator. This is called dynamic range. So we can adjust the power, or we can use attenuator, or we can use a weaker transmitter. Some smart aleck will say, well, you can do some damage to the fiber, but I don't recommend that. But yeah, you can use an attenuator. An attenuator reduces the power in the link, and it's adjustable. So we've got our receiver and our fiber. We add an attenuator, and then we have our transmitter. So it can be fixed or it can be variable.